This is the interim presentation for ME 452 by Team 1, Analysis and Redesign of a Manual Juice Press. The manual juice presser is a tabletop device used to extract juice from fruits such as lemons, limes, and oranges. The user places a pre-cut piece of fruit into a perforated press cup and pulls down on a lever arm which amplifies the applied force and allows the pressing head to squeeze the fruit. The extracted juice flows through the holes into a container below, while seeds and pulp are retained in a strainer. A manual juice press is a widely available consumer kitchen product, sold through global retail and commercial supply channels. Market forecasts estimate that low-cost products, typically $20 to $80 per unit, are to have an annual production of 500,000 to 2 million units per year. The primary consumer group is household users who use the product in their kitchens to prepare fresh juice. These users primarily value ease of use, affordability, compact size, and easy cleaning. The secondary consumer group is small commercial users, such as cafes or juice bars. These users place greater emphasis on durability, efficiency, and the ability to withstand repeated daily use with higher throughput. The exploded view is shown here and consists of 16 unique parts, excluding fasteners.
Function of the mechanical juice press is to extract the juice from the user's choice of fruit. The first primary basic function is to hold the fruit, which is accomplished by securing and then positioning the fruit in the desired location. The second primary basic function is to separate the juice by removing the pulp and retaining the seeds in a device. The juice press will assure dependability to the users by eliminating any splash the fruit may excrete by guarding the exposed end of the fruit and then channeling the juice. The juice press will also assure dependability by maintaining its structural integrity over numerous uses. To provide convenience to the user, it will have an adjustable height to allow for many different cup sizes to be used to catch the extracted juice. By adjusting the capacity and size of the holder, the juice press will be enhanced to be able to accommodate for many different sizes of fruit. And to please the senses of the customers, it will enhance its aesthetics visually to appeal to the user. The functional component mapping matrix shows the functions of each component or assembly in the juice press. Each component has a minimum of 1 and a maximum of 3 functions correlating to it. This verifies that every component on the juice press has a critical and functional role to the task.
The quad chart classification for DfM ranks an item's manufacturing cost and functional importance. Each item in the bill of materials is color-coded, and this corresponds to its position in the quad chart.
For the product family, the functions that would be different between the primary and secondary customers were determined to be supporting capacity, maintaining integrity, and enhancing aesthetics for comfort during repeated use. Our suggestions were a redesigned base and handle for increased stability. This is represented by designating the base assembly and the handle knob and covers as modules.
The CAD redesign between the primary and secondary customers focuses on, for the base, redesigning the area to make it more stable, and for the handle, improving the ergonomics by adding ridged grips for your finger. The square on the base is a common interface. It's the same size and accepts the same size bolt. The hole for the grip is also the same size, and it allows easy interchangeability.
Now we will move on to the product family assembly diagram. On top, as you can see with the original sequence, each variant goes to the full parallel subassembly line. Because the base, holder, and handle differ between household and cafe variants, this identity is locked in from the very first subassembly, forcing 2 separate manufacturing lines. In the modified sequence below, we pulled all of the common parts, anchor, joint, bracket, and the linkage of these into a shared platform that gets built first. At the differentiation point, the line splits and the variant-specific modules, base, press cavity, and handle, are added last through these common interfaces. This lets us run a single platform line and branch off at the end, which cuts over, changeover, and tooling costs in half.
After calculating the assembly times for each component in the juice press, the components with the highest times within the platform and the modular groups were selected for redesign, specifically the bracket for the platform and the handle for the module. Applying the DFA guidelines shown in the following slides led to a reduction in assembly time of roughly 20%, which in turn increased overall assembly efficiency by about 17%.
For automated assembly, we selected the press cavity subassembly consisting of the strainer, holder, and funnel. These parts are small, lightweight, and frequently handled, making them well suited for high-speed automated feeding and insertion. Additionally, these components fall in high functional importance regions of the quad chart, indicating strong potential for DFA improvement.
The redesign focuses on reducing assembly complexity and improving automation compatibility. First, a lip was added to the strainer to improve orientation during feeding, following DFA 7. Second, an internal tab was removed to simplify insertion geometry, following DFA 8. Lastly, the holder and funnel were consolidated into a single component, reducing part count following rule DFA 1. These changes directly target feeding and insertion challenges in automated assembly.
Assembly costs reduced from 11.25 to 3.56 cents due to part consolidation, improved orientation efficiency, and fewer feeders. The redesign does not negatively impact product function as the combined holder and funnel maintains the same juice guidance and containment role. Manufacturing cost is reduced due to lower part count and simplified geometry, while assembly cost is significantly reduced through fewer feeding and insertion operations.
The first part we looked at for process selection was the redesigned bracket with the snap fit feature and reduced fasteners. It's made of 304 stainless steel. It's a 3D shape with holes. Has a massive 350 grams section thickness of 10 millimeters, tolerance of plus or minus 0.1 millimeters. The surface roughness is not applicable with an economic batch size of 500,000 units. You can see in the table when applying these specs and checking them against various manufacturing processes, we decided on machining as being the most capable process, though it is noted that it's not super ideal for the batch size because it is such a large batch, but taking into account all the other specs and taking a look at all the other processes, we did decide to go forward with machining. The second part looked at for process selection was the redesigned handle with only the holes going through that second rung with the new snap fit feature added. Now this handle is made out of A3 aluminum and weighs a bit less than the bracket. So when checking against the manufacturing processes in the table, we actually landed on die casting as our process for manufacturing the handle. There's a note to be made, however, about some of the holes, depending on the effectiveness of the die, may need to be done with secondary machining.
The preliminary bracket design was analyzed using the DfM Pro software, which highlighted the use of filleted edges, a flatly drilled hole, and a small hole to center edge distance. These features were not meeting best practices of having chamfered edges and using hole geometry that fits the tool used. This part is manufactured using a CNC mill and costs an estimated $350 per part with an assumed volume of 500,000. The new design incorporated a through hole for ease of manufacturing, chamfered edges, and a large pre- and post-DMF designs were quoted online to compare with the analytical calculations using hubs. The key takeaway to note is the cost reduction in pre- and post-DFM aligns with the hand calculations. A caveat to note is that Hubs Online was limited to a quote of 100 parts, which is significantly lower than the expected part count of 500,000.
The handle, redesigned after the DFA process, was estimated to cost $1.61 per part given the dimensions shown. The handle was put through the DFDC process to reduce overall cost of die casting the part. The three changes included maintaining uniform wall thickness throughout the shaft, pivot holes opened as upward slots to avoid side pulls, and increasing fillets to reduce corner sharpness. This decreased the total cost to $1.34 per part.
As we compare the manufacturing cost pre and post design, we can see that it decreased from $1.61 per part to $1.34 per part, which is about a 17% reduction, primarily due to the reduced material usage, improved wall thickness, uniformity, and simplified die casting geometry without compromising function.
Introducing an associated app for the manual juice press creates a product service system that enhances both customer experience and sustainability. The app would offer tailored, model-specific recipes for the household and commercial variants, while also enabling users to share their own creations and build a community around the product. It would focus accessory purchasing by showing only compatible strainers, bottles, and handle options, reducing trial and error costs, and extending the useful life of the press. Environmentally, the PSS helps reduce waste by providing tested, reviewed recipes that guide users toward accurate ingredient quantities and promote efficient use of produce. Together, the integrated app and hardware create a more convenient, cost-effective, and eco-friendly juicing experience.